Right, good morning, guys. Today's class is regarding our radiation. This is the fifth unit topic for heat transfer. So far, we are already done with the concepts regarding conduction and convection. We defined what is a conduction, the basic law governing the conduction. The same way we defined convection, the laws regarding convection. We also completed the forced and the natural part of convection. We dealt with the heat exchanger parts and the phase change happening in the convection part, which is radiation, which is boiling and condensation. Now, the last topic here we are dealing is radiation. We obviously know what is radiation is, which we already gone through. Radiation is a mode of heat transfer which takes place even when there is no medium or contact between the two bodies. That is what radiation is. But how this radiation happens and what are the laws which are governing this radiation, we'll see deeply here. Okay. As I mentioned, that radiation is defined as it is a transfer of energy across system boundary by means of an electromagnetic mechanism, which is caused by temperature difference. That means we know radiation should transfer from one place to another place. Sorry. We know radiation should transfer from one place to another place. Here, this happens by only the temperature difference, and this transfer is in the form of electromagnetic mechanism because radiation we need radiations that we have x-rays, we need gamma rays, we know those are all radiations. Here this is the radiation which is related to the heat transfer form. So when there is some temperature difference here, the energy is transferring from system boundary across the system boundary by a means of an electromagnetic mechanism. But whereas for conduction and convection, this to heat transfer to take place, we need the presence of medium. But radiation heat transfer does not require any medium. Okay, we are familiar with it. But for both conduction and convection, we need medium for the heat transfer. But for radiation, there we don't need any medium. And also, a radiation exchange, in fact, occurs most effectively in vacuum because there is no medium. Still, the energy is transferring. That itself is reminding us that the heat transfer rate is very effectively done in the vacuum. The best example we can take for radiation is our sunlight. We know that sun is very far from the earth, but still the radiation from sun travels very fastly at a rate of in the form of light at a rate of 3 to 10 power 8 meters per second. It it takes only 8 minutes of time, and approximately 8 minutes of time for the sunlight to reach from sun to the earth's surface. You can see how fast the radiation is traveling in the vacuum. Further, the rate of heat transfer by conduction and convection varies with temperatures to the first power. We know the governing laws. For convection also we have written that Q is equal to HA delta T. The same way for conduction we wrote H is equal to Ka delta T or Ka dt by dx. There the temperature difference is in the first power. But for here radiation, it is in the fourth power. That means delta T power 4. We know the formula for Stefan Boltzmann. It is Q is equal to sigma A delta T power 4. For previous both conduction and convection, it is only the first power. But for radiation, it is fourth power. Okay. Next, both the amount of radiation and the quality of radiation depends upon temperature because as it is the heat transfer, it will definitely depend upon the temperature. The dissipation from the filament of vacuum tube or heat leakage through the evacuated walls of thermoflask are similar examples of radiation. That means there's some heat leaking from a vacuum tube or the thermoflask. We know thermoflask, right? In which we store the tea or some hot things or any cool water or something. Heat transfer from that also are examples for radiation. So basically we need to define radiation as something which travels heat from one place to another place even there is no medium, and this happens by electromagnetic mechanism. And in conduction and convection, it depends upon the first power of the temperature difference, whereas in radiation it is the fourth power of the uh, temperature difference. Okay. We'll see how these radiation actually taking place. The energy which is radiating services release is not continuous in the form of successive and separate packets or quanta of energy called photons. I think we are very familiar with the word photons, right? It is a it is a bunch of atoms or any energy which are in packed form, which are not continuously emitted, which will be which are not continuous. They are non-continuous and flow in, in separate ways. Those are photons. So the radiating surface will always emit these photons from the surface to the environment. And now these photons propagate in the space. Oh no, this is a radiating surface. Here we have some electrons and atoms. When we have any exciting state here, the photons here will excite and they'll move, which are not in a continuous form, they move in a separate ways. And this propagate into the space as rays. Like we are no rays, right? They propagate into the space as rays. And these movement of rays will create some waves in the space. Means if you see, if you have a room of 100 people, if any 10 people have create some disturbance, it will create the total 100 people disturbance. That means 10 members fall down, the remaining 90 members will also affect with that. That is what wave propagation is. At any one point, you will have any changes, it will propagate in the form of a wave. Here, we'll have that propagation in the form of electromagnetic waves. And this photons will travel which with a speed equal to that of light, which is the 3 into 10 power 8 meters per second in a straight path with unchanged frequency. When they approach the receiving surface, there occur conversion of wave motion into thermal energy. That is what happening. This is something which is related to solar energy sector. That means if you take, we have a sun. From sun, we having some energy coming to the surface in the form of light. Now, this is a radiating surface. We have sun energy coming in the form of light. It touched or it impelled on the radiating surface. Here on the radiating surface, we have some photons. Now these photons got excited. They propagated to the space in the form of waves. These waves are electromagnetic waves, and they flow or they propagate with the velocity equal to light, and they reach the receiving surface. And here the receiving surface will convert this wave motion into thermal energy. That means in the form of heat. This is how we are converting the light energy from sun to thermal energy. This is an example of radiation which is happening. But on the receiving surface, the energy in the form of wave motion should be received by the receiving surface, which might be partly absorbed or reflected or transmitted through the receiving surface. That means if the energy in the form of wave is impelling on the receiving surface, there is no need that complete energy should be absorbed. Okay, only partly can be absorbed or completely uh, reflected or completely transmitted. I'll choose it. Absorbing means the light coming and some of it which is absorbed here. Reflected means the light came and it is reflecting back. Okay. Transmitting means the light or the wave motion came and it is transmitting through the body. This is what these three things may happen, and it depends upon uh, the, the the instant of time or the receiving surface, the material of the receiving surface or the radiating surface materials. This is what these three things can happen. It can partly absorb, it can be reflected, or it can be transmitted, depending upon the material of the receiving surface or anything. Now, all types of electromagnetic waves are classified in terms of wavelength. They are classified in the forms of wavelength. We know what is a wavelength, right? If it is forming in the form of a wave, we have crest, the topmost position, and we have trough. Wavelength is something, it is the distance between two crusts. That means it is the distance between adjacent to two crusts is defined as our wavelength. You know that, right? The topmost is defined as crust. So those two, the distance between those two crusts is defined as a wavelength. So the electromagnetic wave depends upon that wavelength, which is propagating at a speed of 3 into 10 power 8 meters per second. Now, the distinction between one form of radiation and other lies in the frequency and wavelength, because every radiation changes, right? As I said, some radiation can be partly absorbed, some can be reflected, some can be transmitted. So there are different types of radiations there. The distinction or the difference between each form of radiation can be done by using the frequency part and the wavelength. which is rated by an equation or relation. C is equal to lambda into F. Okay, you know lambda, it is a wavelength. F is our frequency. C is a constant which we want speed of light. If you take it as the speed of light, it is our 3 into 10 power 8. C is here, which is a constant value because we are considering the propagating wave having a speed which is equal to approximately equal to speed of light. So this is C is 3 into 10 power 8 meters per second. This is our wavelength and this is our frequency. Okay. Now, as we know, there are different types of radiations depending upon the wavelength and the frequency. On which actually on what characteristics these radiations are differ means they depends upon the nature, temperature, and the state of an emitting surface, the radiating surface on which the light is impelling. It depends upon the nature of the surface, the temperature of the surface, and the state of emitting surface. Okay. However, the gases also depend upon the thickness of the emitting layer and the gas pressure. If you're talking about gases, they also depend upon the thickness of the emitting layer and the gas pressure also. Now, these different radiations, which depends upon the wavelength, are classified into so many types. Now, we'll see what are those. If you see, this is our wavelength part, ranging from 10 power minus 5 to 10 power 4. Here we have in the range of 10 power 5 to 10 power 4, we have gamma rays. In the range of this 10 power 4 to here from 10 power minus 2, we have X-rays. Here you have ultraviolet rays. We have here in the positive form, we have infrared rays. We have thermal radiation. We have microwaves. In between this 0.40 to 0.70, we have our visible light. The light which we can see through our naked eye is that visible light is in an order of 0.40 to 0.70 wavelength. This is our spectrum of electromagnetic radiation. Of all this, now we are interested in our thermal radiation part because that is what we are defining. It is in an order of 10 power minus 1 to 10 power 2 wavelength. Now, in between this, we can see we can observe some thermal radiation, and these thermal radiation will be on the emitting surface. This emitting surface will release some photons. These photons will propagate in the form of wave, which is the velocity which is equal to light, and this will be uh, received by the surface. And that surface, you can have three possibilities. One can be partly absorbed, the other can be reflected, the third one can be transmitted. And there, that receiving surface will convert this wave motion into thermal energy. Okay, this is what the basics of